Okay, so if you've come this far, you must be keen to learn about Suzuki DR650 Preload. It's not an overly complex topic. I mean, there's two things you probably are keen to learn. So the spring rate, so that's just the kilograms per millimeter your spring moves, and there's preload. And they're quite different concepts, albeit they're related. And I'll show you that on the way through the video. And so the key is the Suzuki comes with quite a soft standard spring. It's about 6.5 kilograms per millimeter, and it comes with almost no preload on that spring, just enough to keep the spring tight and stop it from rattling about. And so you can't really do much with that spring, and I'll show you why it's a bit soft for the majority of riders today. I'm fairly heavy at about 95 kilograms, and so that spring is really just too soft for me. It doesn't give me a lot of play, and I'm riding down at the bottom of the spring a lot of the time, especially when I've got some of my touring equipment on the bike. So what I'll do is I'll run through this. As I said, it's not overly complicated, but it does involve graphs and some equations, and so I'll try and be as clear as I can. And if there's any questions or comments, feel free to put them in the comments section, and I'll try and answer any that I can. So the first thing is I'd like to call out ProCycle US. They actually did a full analysis of rear wheel travel versus spring travel for the DR650SE. I think it was a 2019 model, and so they've given us the ratios between how the wheel travels and how the spring travels in all the spring travel information. So that's really helpful. So that's a good entry point for this. So I'd suggest the first thing you do is go to ProCycle US and then have a look at the rear shock travel and the linkage ratios. So that's where we'll start today. So this is the table you get from ProCycle. They've measured rear wheel travel versus spring travel. Now I've plotted spring travel as the x-axis and wheel travel as the y-axis, and you'll see why in a minute. So here's the deflection curve that you will get from using that ProCycle data. So along the bottom here is the rear shock deflection, and along the y-axis or the left-hand side is the rear wheel deflection. And you get this relationship here. And the first thing you notice is due to the linkage, it's not quite linear. It starts to fall away at the top and starts to roll over as the linkage kicks in with a different geometry. But that's not that important for what we're trying to do. So the first thing is you'll notice on the ProCycle website is they say that around about 155 millimeters you'll actually hit the top of the rear bumper. So at that point your spring will compress and the rear bumper will start to come into play. And then round about 235 millimeters wheel travel, or 9.25 inches, you'll actually hit, there's a hard metal rubber bumper coil sleeve, and so your shock can't actually deflect any more than that. So that's actually a hard stop. ProCycle took out that and went to 260 millimeters wheel deflection, which is 119 mil deflection for the shock. But interestingly, they also report the shock will go up to 124 mil. That's the total distance. So I just extended the graph one more step there, but you can't get to there anyway. You have to stop at about 9.25 inches or 235 mil. So using this, that is the relationship you've got between the rear wheel deflection and the rear shock deflection. Now the reason I plotted rear shock on the x-axis is I actually want to convert that to force. So when I put a force on the bike, I want to see what the rear wheel deflection is, so then I can use my that to calculate my sag and my actual ideal sag on the bike. So if you read the internet, it does say you want about 1/3 of the shock to sag when you've got the bike normally loaded. So ideally you'd want about, if you go from 9.25 inches or 235 millimeters deflection, 1/3 sits down here at about 78 millimeters, which gives you about 3 inches. So ideally you want about 3 inches sag for the weight you want to carry, and that's another issue that we need to talk about, is what weight do you want to carry, because there is no one way. You know, some days you might be wearing lots of clothes, some days you might be not wearing clothes, you might be carrying luggage. So again, that's a single point depending on what you're doing for the day. So, but anyway, so it looks like from all the data, your maximum wheel deflection is 9.25 inches or 235 millimeters. And you ideally want about 78 millimeters or 3 inches sag for the weight that you want to carry. And that translates into about 32 millimeters of shock movement. So when you're sitting on the bike at 32 millimeter shock movement, you've got the rest of the shock to compress up to about 104 millimeters shock. So you can go from 32 to 104 theoretically. But when you hit the top of the rubber bumper, remember, this starts changing the spring as well. So as I covered previously, the issue we have now is that's a complicated linkage, and so it's actually quite difficult to work out what the force ratio is between the weight on the rear wheel and the force on the shock. So the way I've done it is reverse engineer it a bit. And so what I did was I calculated on the right hand side of this, you can see how I've calculated the various weights. So the wet weight of the motorcycle by itself is about 166 and probably about 60% on the rear wheel. So that's about 100 kilograms on the rear wheel. And then if I sit on the bike with all my gear on, I'm about 100 kilos with all my gear on, maybe 110 with all my motorcycle gear on, it's about 170 kilos. And then you've got, if I carry 50 kilograms of gear, it's mostly over the rear wheel. And so that's about 210 touring. So they talk about static sag, race sag, and I've added there touring sag. So that's what our 3 weights will be, that you'll see how I'm going to use that. So the first thing is I sat on the bike, and I'll show you that in a minute. And I measured what it was, the bike, just by itself. Okay, so that's the bike jacked up on the motocross stand or whatever you call it, and I'll measure the distance from the bottom of the pannier here to the swinging arm. Now the reason you can't measure the distance to the floor is when you jack the bike up, obviously the tyre expands downwards, so you'd be a little bit off if you did it that way, which I tried originally. Okay, so the distance from the bottom of the rack to the spindle is about 310, and the wheel is definitely off the ground, so that's 310 millimeters to the center of the spindle. If you look at the shock is basically fully extended, and the spring has obviously got a little bit of preload on it because otherwise I could turn it, which I couldn't do there. So what I'll do now is I'll let the bike back down, I'll let it settle on its rear wheel, and we'll remeasure what the distance is. So there's the bike now sitting with its own weight. The distance under the arm's about 245 millimeters. And so that's just sitting by the bike weight, it's alone. So it's dropped about 60 millimeters just by the bike weight, which seems to be quite a lot actually. But anyway, it's 245 millimeters. The arm has, the rear swinging arm was raised just by dropping it on its own weight. The next measurement will just be by the bike and me sitting on it. So that'll be a bit more difficult. So I'll have to see how I'm going to do that. And so the 100 kilograms sitting by itself, the rear wheel deflected about 60 millimeters. And then I sat on the bike and the rear wheel deflected 115 millimeters. So if I plot 100 kilograms and 60 and 170 kilograms and 115, I get this relationship here. You draw a line through it using the spring deflection of 6.5 kilograms a millimeter, which is the standard spring Suzuki supplies. And you get this line here, which looks like it's got about a 10 kilogram of wheel preload, which is about 18 kilogram shock preload on the motorcycle. And so you say, okay, but how do you know that was 18 kilograms of shock preload? Well, I know that for 60 millimeters of wheel deflection, I get 24 millimeters of shock deflection. And for 115 of wheel deflection, I get 48 millimeters of shock. So just using those relationships, so I get 48 millimeters of shock deflection for 170 kilos. That gives me 1.87 kilograms a millimeter. And for 24 millimeters deflection, I get, for 100 kilograms, I get 1.67 kilograms a millimeter. Now, the reason these are different is because that linkage is very complicated and the leverage is changing constantly. And so you look at that picture and you go, there's no way that's a constant leverage. So that leverage will be changing as the geometry changes. Plus, I might not have my kilos quite right. But anyway, you get the idea. And it looks like the ratio is about 1.8 kilograms of shock force to wheel force or wheel weight. And so that's the ratio I'm going to use. I'm going to use this ratio of about 1.8. So if I put 100 kilograms on the back wheel, it's pushing about 180 kilograms on the shock. And that's the ratio I'm going to use. So you can see there what we've got is that looks like the shock relationship for my bike, which is a brand new DR, 6.5 kilograms per millimeter of spring. As weight is put on the rear wheel deflection is up here, and that looks like the relationship, and it's got a little bit of preload on it. And that's probably just to take the slack out of the spring. I actually measured the spring and it was about its full length, so there's just a little bit of tightness on the spring to stop it rattling about, and then it starts to move up that curve as weight goes on the bike. But you can see there I'm getting 60 millimeters movement just with the bike, and I'm getting 115 millimeters movement with me in the bike, so that spring is basically too soft. Recall I said you needed about, I think it was 80 millimeters, 70, 80 millimeters with me on the bike if ideal, so that spring is just too soft. The bike's just sinking too or sagging too much with my weight. So I'm a fairly heavy guy. I have heard that the Suzuki's been designed for about a 75 kilogram person or something like that, and so that spring is basically too soft. So if I take this graph now, so that's the relationship from the previous, it's exactly the same graph, weight on the rear wheel here versus the rear wheel deflection on the left. And there's the 100 kilogram static sag. There's the 170 kilogram rider sag or race sag. And there's the 210 kilogram touring sag. So you can see there, if I get a shock set up as it is, it's actually sitting here as soon as I get on the bike. So you can see here within 45 millimeters of rear wheel deflection, I'm actually going to be sitting on the rubber. And then what happens is it's actually no longer linear, that spring, because you've actually got this spring in the rubber. So below where the spring hits the rubber, it's the spring rate only, so that's your linear portion if you want. But as soon as you hit the rubber, you actually change the characteristics, because it's no longer your spring rate, it's your spring rate plus your rubber. And so your graph actually would deflect like this. And so there's a point, it's called the limit of proportionality point, I think. And so what happens is, as soon as I hit about 155 millimeter wheel movement, it hits my rubber, and I'll start moving up this red line till I get to my maximum point somewhere. And that's a theoretical point, because I don't know where that red line, I don't know what the behavior of the spring plus rubber is. I only know there is a spring plus rubber, so it's going up here, but I don't actually know what that line looks like. And so if I'm sitting on the bike myself, I've got about 45 millimeters before it hits the rubber. If I load all my gear up, so I've got my touring sag, as I call it, it's actually only about 20 millimeters before I hit the rubber. So I've only got about 20 millimeters movement. So basically I'm riding on that rubber all the time when I'm touring, because as soon as the wheel compresses 20 millimeters, it's on the rubber. And so you can see there how that's more confirmation that I really need a stronger spring on this Suzuki. Okay, so let's have a think now about how you design a stronger spring. So let's go to a similar graph again. So I already said that for an ideal third of sag of 80 millimeters, I want my weight and the bike's weight 170. So for 170 kilos, I actually only want the bike to sag about 80, and that'll be using a third of the spring. So that relationship there is the one that defines what the spring weight should be for my weight. Now, I don't want to design it for myself plus all the gear, because if I do that, it's going to be too hard when I ride it by myself. And so really what I want to do is I want to design the bike for myself and the bike, and then when I load some gear up, it will just sag a bit more, which is acceptable. So if I designed it for an 80 millimeter point, that would give me 75 millimeters rear wheel movements before it hits the rubber, and so it would give me a much bigger range for riding. So what I want to do is design that point there. And so the question is, what size of spring do I need? So the blue line, the thin blue line, is the size of spring that I would need for my weight and that sag, or rear wheel deflection, ideal sag for my weight. So the dark blue line above it is the 6.5 kilograms per millimeter. I actually want a heavier spring down here. And so I now need to work out what that heavier spring is. And what I'm going to give you is a magic formula to work out that number. So it's quite an easy way to work it out. So there's a small preload on. That's the deflection I want. So that's the linear portion. And then of course we'll hit a limit of proportionality off here, and that'll hit the rubber, and the red line would then it'll go on some sort of red line. So what I want to do is I'm going to work out what spring rate is for that point, and that's quite an easy formula. So that's the next section. So this is the spring rate magic formula. So if I want a third spring compression, a third of the spring is about 32.46 millimeters, so you can see where that is in the equation. And the other part is just a straight line. It's basically a straight line with a 10 kilogram rear wheel preload. So the design weight minus 10 kilograms for the preload times 1.8, which is the force on the rear wheel to the force on the shock, divided by the current distance of a third of the spring, gives you the spring rate. And as I said, it's just the equation of a straight line rejigged to come up with the spring rate. And so if I look at the example I gave you, I had 170 kilos myself in the bike, minus 10 kilos for a small preload once I've got the the spring tightened up, times 1.8, that's rear wheel force to spring force, divided by 32, which is a third of the spring rate, divided by 32, which is a third of the distance the piston can move. So that gives you about 8.87 kilograms a millimeter. So really I need a spring of about 9 kilograms a millimeter. I think they come in full kilometers. So if I went down to 8, I think it would be going too far. And so probably better just to go up to 9. And then that takes me a little bit between my race sag and my touring sag. So it'll just give me a bit more distance till the spring hits the rubber bumper. And so that's the formula. It's not a hard formula. Anybody can use it. So just work out what you think the weight on the rear wheel is, which is the design weight. Take off 10 kilograms for a little bit of preload. And then you can work your ideal spring out for your weight. As I said, mine is 170 minus 10 times 1.8 divided by 32. And so I get about 8.87 kilograms a millimeter. And that's it. So I need a 9 kilogram spring for my bike to work perfectly for me, and so that's what I'll work on now. So while I'm at the bike, I'll just have a look at the preload that might be on it. So here's a picture of a spring. If you've got 0 preload, it should equal the length of the spring. If you've got a lot of preload, you obviously start to get positive preload. You don't want negative preload, for your spring will flap about and rattle. And so, you know, if I look at what Suzuki recommend, Suzuki say that the softest setting is 10 inches, so I'm guessing the spring is just slightly bigger than that. And the strongest setting is 9.4 inches. And you can see there's not much difference actually between the preload setting. And in fact, if you think it's a 6.5 kilograms per millimeter spring, the issue that you can see there immediately is if you take 253.5 minus 238.5 equals, so it's only 15 millimeters difference between the hardest and softest setting times 6.5 equals that's 97 kilos at the spring. So that's 100 kilos preload you can set on this spring if you want, which does seem quite a lot actually, but you can see there how quite a small movement does translate into quite a big force at the spring. So 100 kilos at the spring. I haven't showed you this calculation yet, but I know that's about 55 kilos at the rear wheel. And so I'll show you that calculation later on, how I got to that ratio. So you can see there I can set up to about 100 kilograms preload on that spring, and I wouldn't recommend that, and I'll show you that later in the video in a later section as well. So there's the bike on the jack, all the weight's off the rear wheel now, and you can see there, hopefully you can see there, the looks like it's about 10 inches spring length when all the weight is off the bike. Okay, so now I've showed you I need a heavier spring. People might be saying, why not screw up the preload? Well, that's exactly what it'd do. It'd screw up the preload. And so preload doesn't change your spring rate. All it does is it changes when your spring will start moving. And to give you an example, I'll just use this graph again. So at the moment, if you look down the bottom left-hand side here, we've got about a 10 kilogram preload. Now this is a wheel preload, so this is a 10 kilogram on the wheel gives you 18 kilograms on the shock. So there's a small preload being applied to this bike already, and as I said, it's probably just to keep the shock from rattling, or the spring from rattling. And so there's a tiny bit of preload. So what happens is your ideal line actually starts away down here, but because you put 10 kilogram preload in, the shock won't start moving until it gets about 10 kilograms, and then it'll start tracking up this line. So if I put 50 kilograms of preload on it, all that happens is it moves the line up to 50 kilograms. So you'd start at this point here, you'd start to put weight on the bike, nothing would happen, it would hit the 50 kilogram point and then start moving up this line. And if I put 150 kilograms preload on it, it would start at this point here, just below 100 millimeters of wheel movement. You'd move along here, so it'd be really hard because you wouldn't be getting any shock movement at all. And then you'd hit this point and then it would move up. So you can see the problem with preload is all it does is it reduces, the more preload you put on, all it does is reduce the amount of movement your shock can actually do. That's all it does. It doesn't change the spring rate and it doesn't change where the curve is. The only way you can change where the curve is change the spring rate, and that'll move the curve to a different place. So preload, you don't want to screw preload up too much because it'll be really, really hard until the spring starts moving. So really what you have to do is change your spring rate with a little bit of preload, and then you've got a nice and pliable bike, and so it'll sag to where you want, and then you'll get the movement that you want back and forward as the bike unloads and loads. So that's what you want to try and do now. So preload, as I said, preload's a bit complicated because it's difficult to get your head around it, but the easiest way to think about preload is it stops your bike from sagging until that weight is applied on the bike. Okay, so that's all I've got today. I hope that was helpful. As I said, going back to the design, that's the point I need to try and get to, which looks like it's about a 9 kilograms per millimeter spring. So I'll get a 9 kilogram per millimeter spring on it. I'll put a little bit of preload on it just to take up the slack in the spring, and that looks like would be ideal for my riding. Now the problem is I haven't worked out what the front forks are doing either, but if the back shock is too soft, I'm going to guess that the front shock is too soft as well. So I'll have to look at what I can do for that. The other issue I noticed is the forks do tend to flex back and forward quite a bit, so I think a fork brace might be the go as well. So I think looking forward, shocks on the DR are definitely too soft and they're designed for quite a light person, and I have heard or I have read it's 75 kilos or something silly like that. And so what I need to do is bump up the spring rates front and rear, and also I need to think about a fork brace. But I think the first thing I really need to do is get this rear shock sorted out. As I said, I'm riding right up near the rubber bumper, so I'm actually riding on the rubber bumper quite a lot as I'm riding along. So I think for touring, I need to think about how I can get off that rubber bumper, and the only way I can do that is an increased spring rate. Okay, I hope this helped people. In the comments, if I've made an error in the maths, let me know. If you want any other explanation, make a comment in the comments and I'll try and help you. I'm just an enthusiastic engineer, and so there could be an error in the calculation, and there could be maybe I've got the concept wrong. I'm always open to suggestions. So thanks very much for watching, and as I said, I hope this helps you design the right spring rate for your DR. Thanks very much.